In this first video, we're going to go over some fairly basic stuff. Or, well, maybe not that basic, but it's stuff that the textbook makes use of that they don't actually explain first, which is a little bit annoying given that this is, meant to be an introductory logic class, and you can't assume that people actually know things like what a recursive definition is. Um, so we'll talk about that in this video. Okay, so we will start with the notion of a set. So a set is pretty much any group of objects. The pretty much will come back to later on, I think. We'll talk about after we go through a few other things about paradoxes and things like that. We can actually talk a little bit about what kinds of things are sets and aren't. But for now, what you can just think of is that a set is any group of objects, right? Any of them count as a set. Um, to write a set, what you do is you take the objects that it contains and you enclose them in curly brackets. So this is the Beatles here, right? You can write the Beatles as the set John, Paul, George, and Ringo. Um, if you want to say that an object is in a set, then you use this symbol here. This is a variant form of the Greek letter epsilon, and it means what it indicates set membership, right? You can read it as is in the set. So this means object X is in the set S. So Ringo is in the set the Beatles, right? Two is in the positive integers. Um, Now, set is defined by its members, right? And not by how the members are described, which is a property that's called extensionality, right? What defines a set is its extension, right? Its membership or the objects that it contains. So, for example, John, Paul, George, Ringo, right? Paul, George, Ringo, John. These are both the same set, right? Changing the order in which you state the members doesn't change the set, which is just kind of the obvious point that if you take the objects that are in a group and then you rearrange them, it's still the same group of objects. Um, and then likewise, if you've got John, Ringo, Paul, Ringo, George, George, Ringo, 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 this is still the same set, right? Repeating the names of members of the set doesn't actually change it, right? Um, okay. If you're thinking of a set as a group of objects, this is going to be misleading in one way, which is that there are certain things that are sets that you probably wouldn't think of as being groups of objects. Um, Okay, first thing is, so you have infinite sets, right? So the positive integers are a set, right? These are the numbers 1, 2, 3, and so on and so forth, right? Those whole numbers are an infinitely large set. Um, Another one is you can have unit sets, right? This is a set that contains only one member. Although it's a little weird to say that, something is a group that only has one member in it, you can actually have a set that only has one member. So, for example, right, that is the unit set containing only Ringo Starr, right, and nothing else. That's the unit set containing two. A unit set and the object that it contains are not the same thing, right? Because Ringo Starr is a drummer from England, and the set containing only Ringo Starr is a set, and sets and drummers are not the same thing, so those are not actually identical objects. Now, the last one is the empty set, and this is the set that contains no members. You could write this as just like a pair of curly brackets with nothing inside, but the convention is that you use a sort of stylized zero symbol to indicate the empty set. In fact, actually, given the way that the numbers are defined, typically zero is actually just defined as the empty set. So the symbol makes sense, right? Because zero and the empty set turn out to be, on most accounts, the same thing. Okay, so that's a basic rundown of sets. And sets, the notion of a set is just something that the book makes use of constantly, right? I think it starts on page 4 when they start talking about sets. Um, The next thing that we'll talk about is the idea of a recursive definition. So recursive definition is a way of defining a set. It's also called an inductive definition. You'll see that particular term sometimes. Um, and what you do in a recursive definition is you define a set by giving a procedure for constructing all of the members of the set. So it's a procedure for going through and establishing what all the entire membership of the set is. And it will have three parts. The first thing that you have is a base case, which just stipulates certain things that fit the definition. Um, then you have an inductive step, which gives a rules. Well, it may just be one rule, but often you'll have multiple rules here, where there are rules for taking something that fits the definition and then turning it into something else that fits the definition. And then you have a proviso at the end that basically just says that this definition is complete, right? That only things that fit the base case or that can be constructed by the inductive step fit the definition. So you've hit all the cases between these two. Okay, so for an example, here is a recursive definition of human. Um, Base case is Adam and Eve are humans. Then the inductive step is the children of any humans are humans. And then we have a proviso, nothing else is a human, right? So chimpanzees don't count as humans, gerbils don't count as humans, right? Whatever other things you have don't count as humans. There are certain theological assumptions that are being made here, but if those theological assumptions are correct, then this definition does pick out all and only the humans that have ever lived. For another example, here's a recursive definition of positive integers. This is actually like the standard way of defining the set of positive integers. You start with your base case, you stipulate that 1 is a positive integer. And then in the inductive step, what you say is that if you have a positive integer and you add 1 to it, then the result of that operation is also a positive integer. So 1 is a positive integer. If you add 1 to 1, then the result of that, which is 2, is also a positive integer. If you add 1 to 2, you get 3, which is a positive integer, and so on and so forth. And between those, yeah, you define the entire sequence of positive integers. And then you just have your proviso, right? Nothing else is a positive integer, right? So, ham sandwiches and 3.5 and -4 and all of those, none of those count as positive integers. So this doesn't come up until chapter 2, right? Because when the textbook starts talking about the language SL, the way that they define the language SL is by giving a recursive definition of the sentences of SL. And the way that the definition works is base case is the simplest possible sentences that you can have. So the simplest sentences in the logical system that we're working with. And then the inductive step just shows you how, if you have a sentence, how you can construct a more complicated sentence out of that. And so this is the definition that they give of what the sentences are, right? It's a procedure that shows you how you could construct all the possible sentences in the language. All right, so with this, then you're basically ready to read up to the middle of chapter 2.